For all of our history, we have been a species defined by a single profound question, a question whispered around campfires and shouted into the uncaring void by our most powerful radio telescopes. It is the ghost that haunts our science, the muse of our fiction, the deep resonant mystery that hums beneath the noise of our civilization. In a cosmos overflowing with 100 billion galaxies, each one a glittering city of 100 billion suns, where is everybody? The universe should be a boisterous, crowded metropolis, teeming with voices, signals, and the grand signatures of life. Instead, what we have found is an unnerving, almost impossible silence. An emptiness so vast and so complete it feels like a declaration. For generations we have listened, straining our electronic ears for the faintest whisper in the cosmic static, a single anomalous note in the symphony of creation. We have scanned the heavens for the light of alien cities, for the hum of interstellar engines, for any sign at all that we are not utterly and completely alone in this beautiful, terrifying expanse. The silence, however, has remained unbroken. A perfect, pristine quiet that stretches from one edge of the observable universe to the other. But perhaps we have been listening for the wrong thing. We have been waiting for a message, a deliberate broadcast sent from one intelligence to another. What if the first evidence of life beyond Earth isn't a greeting but an accident, not a shout but a relic? What if it arrives not as a signal carried on waves of light, but as a physical object, a piece of flotsam carried on the slow, inexorable currents of the interstellar ocean washing up on the Posa shores of our own solar system? For eons, our sun has been an island, its family of planets orbiting in splendid isolation, untouched by anything from the outside. That comforting illusion was shattered in 2017 with the arrival of Oumuamua, the first confirmed visitor from another star system. It was a scout, a strange, elongated enigma that tumbled through our neighborhood too quickly for us to truly understand it, leaving behind more questions than answers. It proved that the space between the stars was not empty but a highway, and that we were no longer isolated. The door had been opened. We knew then that others would follow. We just didn't know when or what they would be. And then it came, a faint, almost imperceptible smudge of light captured by the digital eyes of the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a network of telescopes tirelessly scanning the night sky for threats. On a routine survey, an algorithm flagged a new object, one whose trajectory was immediately wrong. This was not a familiar neighbor, not an asteroid from the belt or a comet from the distant Oort cloud, bound by the familiar gravitational embrace of our sun. This object, designated 3I, Atlas, was moving with a purpose and a velocity that screamed of a different origin. Its path was a hyperbola, a perfect open-ended arc that meant it was not a captive of our star. It was a traveler passing through a celestial tourist on a one-way journey that began somewhere in the unimaginable darkness between the stars, and would end in that same darkness, never to return. Like Oumuamua before it, this was a messenger from the void. But this time, it was different. This time, we were ready. An army of instruments, both on Earth and in orbit, swiveled to stare at this new guest, hungry to decode the secrets it carried from its ancient unknown home. From the very beginning, 3I, Atlas refused to behave. As astronomers tracked its progress, the data that streamed back was a cascade of contradictions, a puzzle that grew more complex with every observation. Comets, the most common type of interstellar wanderer we expect to see, are essentially dirty snowballs. As they approach a star, the heat vaporizes their ice, creating a brilliant glowing halo called a coma, and often a spectacular tail of gas and dust that can stretch for millions of miles. Telescopes were trained on 3I, Atlas, expecting to see this telltale sign of outgassing the celestial breath that would betray its icy nature. But there was nothing. A frustrating, stubborn lack of activity. It was inert, a silent rock gliding through the solar furnace without so much as a wisp of vapor. This alone was unusual, suggesting it was perhaps a dry, rocky asteroid, but its trajectory held another secret, a far deeper anomaly that sent a quiet shockwave through the astronomical community. As 3I, Atlas, continued its plunge towards the sun, its path began to deviate. The change was minuscule, a whisper of a nudge on a cosmic scale, but it was undeniably there. It was accelerating, but not in a way that could be explained by the sun's gravity alone. It was being pushed by some other force, a gentle, persistent pressure that was altering its course. For a comet, this is normal. The outgassing of jets of vapor from its sun-warmed surface acts like a set of tiny, unpredictable rocket thrusters, a phenomenon known as non-gravitational acceleration. But 3I Atlas had no jets. It had no coma. It was displaying the times-effect times of a comet without any of the visible causes. It was a ghost in the machine, a physical impossibility playing out in real time against the backdrop of the planets. It was being propelled by a phantom force. The object was dark, far less reflective than a typical comet or asteroid, absorbing an unusual amount of the sunlight that fell upon it. And strangest of all, as it rounded the sun and began its long journey back out into the void, it seemed to fragment. Not in the violent, explosive way a volatile comet might, but almost gently. It broke apart into pieces that continued along the same impossible, subtly accelerating path. What could explain this cascade of contradictions? A dark, inert object with no visible outgassing, yet one that was clearly being pushed by a mysterious force, a force powerful enough to alter its path through the solar system and eventually tear it asunder. The list of natural explanations grew thinner with each new piece of data. Could it be a body made of solid hydrogen, an exotic object theoretically possible but never before seen, whose invisible vaporizing gas could provide the push? Perhaps. Could it be an object with a bizarre shape and composition unlike anything we have ever conceived? Possibly. Science thrives on finding naturalistic answers to confounding questions. But as the familiar explanations were exhausted one by one, a few scientists began to entertain a thought so audacious, so far beyond the pale of conventional thinking, that it felt more like science fiction than academic theory. A thought that, if true, would not only solve the riddle of 3I Atlas, but would also answer that other older question, the one about the great cosmic silence. To understand their hypothesis, you must first let your imagination soar to a scale of engineering that dwarfs anything humanity has ever conceived. Picture a civilization far older and more advanced than our own, a civilization that has endured for millions of years, its population and energy needs growing exponentially. They would eventually face a fundamental limit. A single planet can only provide so much energy, so much living space. Their ultimate resource, the one that makes all life in their system possible, is their star. And for a truly advanced intelligence, the thought of all that stellar energy, that titanic thermonuclear furnace radiating uselessly out into empty space, would be an act of unforgivable waste. So they decide to capture it. All of it. They begin the greatest construction project in the history of the universe. They start to build a shell around their star. A vast artificial sphere composed of countless orbiting platforms, a habitat and energy collector on a planetary scale. This is a Dyson Sphere, a concept born from physics, a theoretical megastructure that would be the ultimate signature of a technological superpower. It would be a civilization that has transcended the cradle of its homeworld and turned its entire solar system into a single contiguous engine for its survival. From the outside, such a system would look strange. The light of the parent star would be completely obscured, blotted out by the shell. The only thing an external observer might detect is a faint, uniform glow in the infrared spectrum, the waste heat generated by the civilization living and working inside. For decades, we have searched for these signatures, these faint heat ghosts in the cosmos, hoping to find evidence of such godlike engineering. We have found nothing. The silence has persisted. But what if a Dyson Sphere is not eternal? What if, after millions or even billions of years, it fails? A celestial impact, a technological breakdown, a war fought with unimaginable energies, or simply the slow, inexorable decay of materials over cosmic timescales. A crack could form, a section could shear off, a single, colossal piece of the most advanced structure ever built could be flung out of its home system by the catastrophe sent tumbling into the interstellar darkness. For eons, it would travel a silent, derelict fragment from a long-dead empire of the stars. It would be dark, made of advanced materials designed to absorb radiation, not reflect it. It would be thin, a vast but lightweight panel like a solar sail. And if such an object, such a shard from a shattered celestial mirror, were to drift through our solar system, What would it look like to our telescopes? It would be inert, showing no cometary activity. It would be dark, its surface constructed for energy absorption. And crucially, as it approached our sun, the gentle pressure of sunlight itself, the stream of photons striking its vast flat surface, would be enough to push it. It would experience non-gravitational acceleration without any outgassing. The phantom force would be revealed not as a phantom at all, but as the simple, elegant pressure of starlight acting on an object of artificial, impossibly thin design. The sun's radiation would be its engine. The object would behave exactly like 3I, Atlas. The fragmentation, too, could be explained. A structure never designed to withstand the gravitational stresses and intense thermal shock of a close pass by a new star could simply buckle and break apart its ancient materials, finally succumbing to forces they were not built to endure. The hypothesis is a perfect, terrifying fit. It resolves every single contradiction in the data with a single breathtaking explanation that this visitor from the stars is not a rock. It is a piece of alien technology. This is an extraordinary claim, perhaps the most extraordinary claim that can be made in science, and it demands truly extraordinary evidence. The idea that we have been visited by a fragment of a Dyson Sphere walks a razor's edge between groundbreaking discovery and delusional fantasy. It is a proposition that forces us to confront the limits of our own understanding and the vastness of our own ignorance. But science is not about believing what is comfortable. It is about following the evidence wherever it leads, no matter how uncomfortable the destination. The data from 3I, Atlas, is a cosmic breadcrumb trail, a set of clues left behind by a silent messenger, and we as a species are now cast in the role of detectives in the greatest mystery of all time. We are being asked to determine the nature of this object, to decide whether it is a strange but natural anomaly or the first tangible proof that we are not and have never been alone. To do that, we must dissect every photon of light ever captured from this enigma. We must analyze its bizarre trajectory model, its fragmentation, and search for any chemical or physical signature that could betray its true origin. The hunt for the truth about 3I, Atlas, is more than just an astronomical puzzle. It is a search for ourselves, for our place in a universe that has suddenly become a far more mysterious and far more interesting place. The journey into that mystery begins now. What if the universe has already sent us a message? Not a signal, not a radio wave riding the interstellar winds, but something more profound. A piece of itself. A bottle cast into the cosmic ocean waiting for someone to find it. What if we found it, and at first didn't even recognize what it was? Our story begins not with a thunderous roar, but with a silent digital whisper. High atop the volcanic slopes of Hawaii, under skies so pure they seem like polished obsidian, a sentinel stands guard. It is the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a network of robotic eyes, their gaze sweeping across the heavens night after tireless night. Their mission is a sober one: to scan for incoming asteroids, the rogue chunks of rock that could pose a threat to life on Earth. They are our planetary defense, our silent protectors, mapping the celestial shooting gallery we call our solar system. On December 28, 2019, while the world was lost in festive slumber, the algorithms of Atlas flagged a new transient, a faint, almost imperceptible smudge of light moving against the backdrop of distant, unblinking stars. To the automated system, it was just another data point, another potential wanderer to be catalogued and tracked. Initial calculations were run, orbital mechanics plotted. The object's trajectory was unusual. It wasn't circling our sun in a familiar elliptical embrace like a planet or a local asteroid. Its path was a hyperbola, an open-ended curve. This was not a member of our solar family. This was a tourist, a traveller from the unfathomable depths between the stars. It had fallen towards our sun from the direction of the constellation Triangulum, a ghost slipping through the gravitational gates of our system, destined to loop once around our star and then depart, vanishing back into the cold black wilderness from which it came. It was given a designation C, 2019Y4, but soon its true nature became clear, and its name was revised, becoming a title far more resonant with Mystery 3I, Atlas. The 3i was the critical identifier. The third confirmed interstellar object ever detected by humanity, a visitor from another star. The world's astronomers turned their most powerful instruments towards the newcomer, and what they saw at first seemed comfortingly familiar. 3i, Atlas, was surrounded by a faint greenish halo of gas, a tenuous atmosphere called a coma. Trailing behind it was a wispy tail, a classic cometary feature. The conclusion seemed obvious. This was a comet not unlike the billions of icy bodies orbiting in the dark fringes of our own solar system, out in the frozen expanse of the Oort cloud. It was, scientifically speaking, a dirty snowball warmed by the distant but growing influence of our sun. As it drew closer, the sun's radiation was boiling its surface, causing ice to sublimate directly into gas, releasing trapped dust and creating its ethereal glow. It was, for all intents and purposes, a classic celestial vagabond. The second of its kind we had ever seen up close after the fleeting passage of 2i, Borisov, just months earlier. Borisov had been a textbook case, a perfect, almost disappointingly normal interstellar comet. It behaved exactly as our models predicted. And 3i, Atlas it seemed, would be its twin, another piece of cosmic driftwood washed up on our shores. To understand why this initial classification was both so logical and so profoundly misleading, we have to pull back to see our solar system not as a home but as an island of light and warmth in a vast cold and dark ocean. The space between the stars, interstellar space, is a void of almost unimaginable scale and emptiness. The nearest star to our sun, Proxima Centauri, is over 4 light-years away. That's a gap of 40 trillion kilometers. For centuries we imagined this gulf as being perfectly empty, but we now know it is haunted by orphans, objects born in other solar systems around other suns, and then violently cast out into the lonely darkness. The universe is a chaotic and dynamic place. Imagine a young solar system billions of years ago, a cosmic nursery teeming with newborn planets. Their orbits are unstable, a gravitational dance of breathtaking complexity. A giant planet like our Jupiter migrates inwards, its immense gravity acting like a celestial slingshot. It can seize a smaller icy world and hurl it with such tremendous force that it escapes the gravitational anchor of its parent star entirely. The planetoid is flung into the abyss, doomed to wander the galaxy alone for eternity. Or picture a catastrophic collision, 2 protoplanets smashing together, shattering into 1 trillion pieces. Most of the debris remains captured by the star's gravity, but some fragments, propelled by the raw energy of the impact, are launched on an escape trajectory, becoming interstellar shrapnel. Even the death of a star, a supernova, can act as a cosmic cannon, blasting planetary remnants across the galaxy. Over the billions of years of galactic history, this process has repeated itself countless trillions of times in every star system. The result is that the space between the stars is not empty at all. It is filled with a slow, invisible blizzard of these outcast worlds. Comets, asteroids, perhaps even rogue planets, all sailing silently through the dark. We are swimming through a ghost river of forgotten solar systems. For all of human history, we were blind to this traffic. These objects are small, dark, and incredibly far apart. The odds of one of them passing close enough to our sun for us to see it were considered astronomically low. Then in 2017, everything changed. A bizarre needle-shaped object tumbling end over end shot through our system. It was named Oumuamua, the Hawaiian word for scout. It was the first, 1i. It was reddish, rocky, and showed no cometary activity, no tail, no coma. Yet it was accelerating away from the sun, pushed by a mysterious, unseen force. It was an enigma that left scientists baffled and remains debated to this day. Was it a nitrogen iceberg, a new type of natural object, or was it something else entirely? Then came 2i, Borisov, in 2019, the comforting counterpoint. It looked and acted just like a comet from our own Oort cloud. It was a sigh of relief for many astronomers. Oumuamua was the anomaly, Borisov was the norm. The universe, it seemed, wasn't quite as strange as we had briefly dared to imagine. And so when 3i, Atlas, arrived just a few months later, sporting its own brilliant coma, and tail it fit neatly into this emerging picture, another Borisov, another simple natural piece of another solar system, the case for a moment seemed closed. A fascinating curiosity, a chance to study the building blocks of another star's family, but ultimately a known quantity. Science had a box for it, a label that read Interstellar Comet. And for a few precious weeks, 3I Atlas sat comfortably inside that box. But the universe rarely cares for our neat and tidy classifications. The cosmos is the ultimate arbiter of mystery, and the more we watched this distant traveler, the more it refused to cooperate. The more data we collected, the more this simple comet began to look impossible. The neat little box we had built for it began to splinter. The story of a simple, dirty snowball started to unravel, replaced by a series of riddles written in the language of physics. And the answers to those riddles would force some of the most brilliant minds on the planet to consider an explanation so far-fetched, so audacious, it had lived until now only in the pages of science fiction. They were forced to ask a question that changes everything. What if 3I, Atlas, isn't a piece of a planet? What if it's a piece of a machine? To even begin to contemplate such a staggering idea, we must journey back to 1960 to a quiet office at the Institute for Advanced Study in Princeton. Here, a visionary physicist named Freeman Dyson was wrestling with a profound question, one that elegantly combines astronomy, engineering, and the sheer logic of survival. His question was this: what does a truly advanced Type II civilization on the Kardashev scale do for power? A civilization that has outgrown the energy resources of its home planet, a society that requires not just a fraction but the entire energy output of its parent star. How would you capture the total ferocious world-forging power of a sun? Our sun, for instance, radiates almost 400 septillion watts of energy every second. The Earth intercepts only a tiny fraction of that, a billionth of the total output. The rest radiates uselessly away into the cold vacuum of space. To a civilization with near limitless technological capability, this would seem like an unconscionable waste. It would be like living next to the world's largest waterfall and only using a single bucket to collect water. Dyson reasoned that such a civilization, driven by the inexorable need for more energy, would embark on the most ambitious engineering project in the history of the universe. They would build a cage for their star. This concept has become known as a Dyson Sphere, and it is crucial to understand that Dyson himself never imagined a solid monolithic shell. Such a structure would be gravitationally unstable and require materials of impossible strength. Instead, he envisioned something more practical yet still breathtaking in its scale: a Dyson swarm. Imagine a civilization disassembling the other planets in its solar system, its asteroids, its moons, mining them for raw materials. They would then use this matter to construct a vast cloud of trillions of independent orbiting habitats and solar collectors. A loose, overlapping lattice that would eventually form a complete porous shell around the star. Each collector, a continent-sized solar panel, would soak up the star's light, converting it into usable energy and beaming it to the civilization living within the swarm. From the outside, the star would gradually dim in the visible spectrum, its light blotted out by the ever-growing cloud of technology. It would become a hidden sun, but the laws of thermodynamics are absolute. Energy cannot be destroyed, only converted. All the machinery, all the habitats, all the computers running this star-spanning society would generate enormous quantities of waste heat. The entire structure would have to radiate this heat away into space to avoid melting. This waste heat would glow not in visible light but in the infrared part of the spectrum. This provides us with a tantalizing, specific and potentially observable signature. If you want to search for the grandest alien megastructures imaginable, you don't look for light. You look for heat. You scan the skies for stars that are unnaturally dim in the visible spectrum, but which blaze with an inexplicable, colossal infrared glow. A technological fever dream burning silently in the dark. For over 60 years, the Dyson Sphere has remained one of the most powerful and enduring ideas in the search for extraterrestrial intelligence. It is the ultimate expression of technological mastery over nature. A civilization that builds a Dyson Sphere has become a true steward of its star, a galactic architect of almost godlike power. They would have harnessed the power of a sun, creating a near-immortal home with effectively limitless energy. But what happens when something goes wrong? What happens to a structure so vast it beggars belief? A machine composed of trillions of independent parts held together by gravity and orbital mechanics. Over cosmic timescales, even the most perfect creation can fail. Imagine an external impact from a massive rogue planetoid, a cataclysmic event punching a hole through the swarm. Or an internal catastrophe, a war, or a technological breakdown that causes a cascade failure, sending sections of the structure tumbling out of their stable orbits. Or perhaps after millions of years, the civilization simply dies out or moves on, leaving their grand creation to slowly decay, a ghost machine orbiting a ghost star. In any of these scenarios, pieces of the structure could be flung away, shards of the great machine ripped from their cosmic anchor, and just like their natural cometary counterparts, ejected into the interstellar void by a gravitational slingshot. Tattered sails of a forgotten starship tumbling through the darkness for eons. Fragments of alien technology indistinguishable from a rock to a civilization that has never dared to dream of such things. This is the heart of the matter. This is the collision point between a strange misbehaving comet from another star and one of the most audacious theoretical concepts ever conceived. 3I, Atlas, arrived in our solar system wearing the perfect disguise. It looked like a comet, it flared like a comet, but it was travelling on a path that defied that simple explanation. It was shedding mass in a way that made no sense for a body of ice and rock. Its light curve was bizarre, its behaviour erratic, almost unnatural. It was as if we were watching a fragment of a natural object, but one that was behaving like a hollow, artificial construction. And so the unthinkable question was whispered first in the quiet corners of astronomical forums, and then in the halls of academia itself. Could this object, this visitor from the stars, be the first tangible piece of evidence we have ever found of alien technology? Are we looking at a comet from a distant dying solar system, or are we looking at a piece of cosmic wreckage, a fragment of a shattered Dyson Sphere, a message in a bottle that tells a story not of geology but of engineering, a story of a civilization that reached for the stars and perhaps fell? The data streamed in from telescopes across the globe. And with every new observation, the mystery of 3I, Atlas, only deepened. Its simple cometary facade was beginning to crumble away, revealing something far stranger and far more profound underneath, something that would challenge the very foundations of what we believe is possible in the universe. And so, with its origin confirmed as a traveller from the void between the stars, the real work on 3I, Atlas, began. The world's great observatories, a global network of glass and steel, turned their collective gaze towards this fleeting visitor. Every photon of light captured was a syllable in a new language, every measurement a clue in a mystery we were only just beginning to comprehend. At first, the story it told seemed comfortingly familiar. Its trajectory, plotted with immense precision, showed a graceful arc dictated solely by the sun's immense gravitational pull. It was a path written in the elegant mathematics of Newton and Einstein, a celestial billiard shot across interstellar distances. For a few precious weeks it behaved exactly as expected, but science is a discipline of relentless scrutiny, a process of poking and prodding at reality, searching for the slightest inconsistency. And deep within the data, buried in the 5th decimal place of its predicted position, the first anomaly surfaced. It was a whisper at first, a discrepancy so small it could easily have been dismissed as an instrumental error or a miscalculation. 3I, Atlas, was not quite where it was supposed to be. It was running hot, moving ever so slightly faster than gravity alone could account for, as if an unseen hand were giving it a gentle, persistent nudge away from the Sunday. This phenomenon has a name: non-gravitational acceleration, and for astronomers it immediately conjured the image of a comet. As a comet nears the sun, its icy surface warms and sublimates, turning directly from solid to gas. This process creates jets of vapor and dust that stream away, acting like tiny chaotic rocket thrusters on the cometary nucleus. This outgassing is the most common source of non-gravitational force we see in our own solar system. It's a natural, well-understood process, the engine that gives comets their spectacular ethereal tails. The mystery, it seemed, was solved before it had even truly begun. 3I Atlas, was simply a comet from another star behaving as comets do. A collective sigh of relief echoed through the astronomical community. The universe for a moment felt orderly once more. The next step was therefore a simple procedural confirmation. To prove it was a comet, all we had to do was look for the coma, the glowing halo of gas and dust surrounding the nucleus, and the magnificent tail trailing behind it. With the awesome power of our new generation of telescopes, instruments, capable of seeing the faintest smudges of light from the dawn of time, this should have been trivial. We pointed our most sensitive eyes towards that specific point in space. We filtered for the telltale spectral signatures of sublimated water, of carbon monoxide, of all the volatile compounds that form the bedrock of cometary chemistry. We waited. We integrated hours of exposure time, stacking images upon images to draw out the faintest of details, and we found nothing. Absolutely nothing. Where there should have been a vast, tenuous cloud of gas, there was only the black, pristine vacuum of space. Where a tail of dust and ions should have stretched for millions of miles, reflecting the sunlight like a celestial banner, there was only emptiness. 3I. Atlas was a ghost. It was accelerating away from the sun with a force characteristic of a highly active comet, yet it displayed none of the physical evidence. It possessed a phantom engine, a source of propulsion that was powerful enough to alter its cosmic path, but which remained utterly maddeningly invisible. This was not a minor detail. This was a profound contradiction. It was like hearing the thunder of a powerful locomotive, but seeing only a single silent boxcar gliding down the tracks. The two pieces of evidence were in direct screaming opposition. The acceleration was real, the orbital data was irrefutable, the lack of outgassing was also real, the spectral analysis was unequivocal. Both could not be true for any comet we had ever known. Astronomers scrambled for explanations. Perhaps it was outgassing pure hydrogen, which would be incredibly difficult to detect. But that would require a body made of frozen hydrogen, a theoretical object so fragile it should have disintegrated long before it ever reached our star. Perhaps its jets were composed of particles of a peculiar size, some dust-to-gas ratio that made them invisible to our instruments. This required special pleading, a fine-tuning of parameters that felt less like an explanation and more like an excuse. Every conventional hypothesis began to fray at the edges, strained by the sheer starkness of the paradox. The object was being pushed, but it wasn't venting gas. It was a ship without a visible sail catching a wind that shouldn't exist. And as this central mystery deepened, another even stranger line of evidence began to emerge. It came from the most fundamental observation one can make of a distant object, the simple act of measuring its brightness over time. This data produces what is called a light curve, the object's unique rhythm, its flickering heartbeat as it journeys through space. For a simple spherical object, rotating the light curve is a flat line. Its brightness never changes. For a more common potato-shaped asteroid, it produces a gentle rolling wave of light as its broader sides and narrower ends alternately face us. The pattern is predictable, stable, a sinusoidal signature that tells you about its shape and its period of rotation. When we first measured the light of 3I, Atlas, we saw just such a pattern, a rhythmic rise and fall in brightness repeating every 9.7 hours. This suggested an elongated object turning over and over with the clockwork regularity of a celestial gyroscope. Once again, there was a momentary sense that order was being restored. An elongated shape was unusual, but not impossible. But the universe rarely offers such simple answers. As we continued to watch night after night, the rhythm began to shift. The 9.7-hour period was not absolute. Sometimes the peaks of brightness were higher than expected, other times they were strangely muted. The smooth, predictable wave began to break, becoming jagged and chaotic. The object's steady pulse was becoming an erratic tremor. This was not the signature of a solid body in simple rotation. A spinning potato does not suddenly change its shape or the way it spins. Something far more complex was happening. The data pointed to a new mind-bending conclusion. 3I Atlas was not just rotating, it was tumbling. Imagine a perfectly thrown football spinning on its long axis. That is simple rotation. Its motion is stable, predictable. Now imagine that same football after it's been kicked end over end, wobbling chaotically through the air. That is a complex tumble. It is a far less stable, far more energetic state of motion. For an object in space to enter such a state, it usually needs a nudge. A collision perhaps, or the gravitational torque from a close flyby of a planet. But 3I, Atlas, was in the empty depths of interplanetary space, far from any source of significant gravitational interference. It should have been in its lowest energy state, a simple, stable spin. Yet here it was performing a complex, chaotic ballet for our telescopes. The only way to reconcile the wildly fluctuating light curve was to model an object with a truly extreme and irregular shape. Not a potato, not a cigar, but something more akin to a shard. A thin, flat, fractured piece of something. A shape like that tumbling through space would present a constantly changing profile to our view. One moment we would see its broad, flat side reflecting a large amount of sunlight, causing a bright peak in the light curve. The next we would see it edge on, a razor-thin sliver reflecting almost no light at all, causing a precipitous drop in brightness. The computer models that tried to replicate the light curve produced fantastic shapes, contorted and asymmetric with aspect ratios, the difference between their longest and shortest dimensions that pushed the boundaries of physical possibility for a natural object. A celestial body this thin and flat should not be able to hold itself together against the rotational stresses of its own tumble. It should have shattered into a cloud of dust millennia ago. And it was here, in this collision of impossibilities, that the ghost of our first interstellar visitor returned to haunt us, the shadow of Oumuamua. The name itself is Hawaiian for scout, a messenger from the distant past. And what a message it had been. Oumuamua, detected in 2017, was the prototype for this very mystery. It too had exhibited significant non-gravitational acceleration. It too had a complete and baffling lack of a cometary tail. And its light curve was the most extreme ever recorded, suggesting a shape that was perhaps 10 times longer than it was wide, a cosmic needle or a perfectly flat pancake tumbling through our system. At the time, Oumuamua was treated as a singular anomaly, a 1 in a trillion cosmic weirdo. Scientists, by their nature, are conservative. They will exhaust every conceivable natural explanation before daring to whisper the alternative. And so elaborate, even desperate theories were constructed. Oumuamua was a nitrogen iceberg chipped from a Pluto-like planet, its outgassing invisible. It was a cosmic dust bunny, an object with a density less than air. It was a hydrogen comet. Each theory was more exotic than the last, and each had significant flaws. But with only one data point, the debate remained academic, a fascinating but ultimately unresolved curiosity. Then came 3I, Atlas. And suddenly, we no longer had a single anomaly. We had a pattern. We had a class of objects. These interstellar visitors, these messengers from other star systems, were not behaving like the comets and asteroids from our own neighborhood. They were fundamentally different. They were small, dark and inert, showing no signs of cometary activity, yet they were actively propelled by a mysterious invisible force. And they possessed extreme, flattened, shard-like shapes that strained the limits of material science. To have one such object appear is a riddle. To have two appear within just a few years of us developing the technology to detect them is a statistic that begins to demand a new kind of answer. The probability of two such bizarre natural objects arriving in our system in such a short span of time was astronomically low. The coincidence was becoming difficult to ignore. The quiet, restrained language of scientific papers could not conceal the growing tension. The established orthodox explanations were no longer fitting the facts. They felt forced, contrived, like epicycles added to a Ptolemaic model to save a flawed theory. You can only stretch a natural explanation so far before it breaks, and the evidence from 3I, Atlas, was pulling it taut. The object's trajectory was impossible for an asteroid. Its appearance was impossible for a comet. Its shape and motion were impossible for any known natural celestial body. In the hushed conversations in university corridors, in the late-night emails exchanged between observatories, a new word began to surface. It was a word laden with a century of speculation and science fiction, a word so profound and so disruptive that most were terrified to even think it, let alone say it aloud. The word was artificial. What if the non-gravitational acceleration wasn't from outgassing at all? What if the gentle, persistent push was the product of something else? Something like the pressure of sunlight itself acting on an object that was incredibly thin, incredibly light, but had a very large surface, area, a solar sail. What if the extreme, flattened, shard-like shape wasn't the result of some freak cosmic collision, but was instead the product of engineering? A fragment of some larger constructed object? These were no longer the musings of fringe theorists. The data was forcing the hand of mainstream science, pushing it to the very edge of what it was comfortable considering. The scientific method demands that we follow the evidence wherever it leads, even if it leads to a conclusion that could fundamentally rewrite our place in the cosmos. The anomalies of 3I, Atlas, the silent push, the ghostly appearance, the tumbling, shattered mirror-like curve, had closed the door on every easy answer. In doing so, they had opened another, a door that leads into a territory of thought both exhilarating and terrifying. We were being confronted with an object that didn't fit into any of our carefully constructed boxes for natural phenomena. And so we were faced with the most profound question we could possibly ask. If 3I, Atlas, was not a comet and not an asteroid, then what was it? For months, the anomaly of 3I, Atlas, had been a ghost in the machine, a whisper in the lecture halls of astrophysics. It was the ultimate academic curiosity, a problem for the theoreticians to chew on a footnote in the grander cosmic narrative. We had traced its impossible trajectory, a solar flyby that should have torn it to vaporous shreds. We had measured its unsettling lack of a coma, the spectral blankness where the telltale signs of outgassing from a comet or asteroid should have been. Yet, for all its strangeness, it remained within the realm of the explainable just barely. The prevailing consensus was one of cautious bafflement, a collective agreement to label it an outlier, a one in a trillion natural fluke whose origins were simply beyond our current models. It was a puzzle, certainly, but a puzzle we could set aside for a future generation to solve. Science, after all, advances patiently, one confirmed data point at a time, and prefers the mundane explanation over the magnificent until it has no other choice. That choice was about to be forced upon us. The first tremor that would shatter this fragile peace came not from a grand announcement, but from the quiet hum of servers at the European Southern Observatory in the high, thin air of the Atacama Desert. Here, the Very Large Telescope, an instrument of almost sublime power, had been tasked with a deep, long-exposure observation of 3I, Atlas, as it receded from our Sun. The goal was simple: to wring every last photon from the faint object and build the most detailed spectroscopic profile ever attempted. For weeks, the data trickled in, a stream of numbers that had to be painstakingly calibrated, corrected for atmospheric distortion, and cleaned of cosmic ray interference. Dr. Ilara Vance and her team worked in the hushed reverence of the control room, their faces illuminated by screens displaying the raw language of light. They were looking for the familiar chemical fingerprints of silicates, of carbon compounds, of water ice, the building blocks of every natural object we had ever studied in our solar system. What they found instead was a message of profound and unnerving clarity. It was a spectrograph of something that had no business being out there. The absorption lines, those dark slashes in the rainbow of light that betray an object's chemical makeup, were razor-thin, unnaturally sharp. This bespoke a surface that was not a chaotic jumble of rock and ice, but something uniform, something with a startlingly pure composition. More shocking were the elements themselves. There were, of course, iron and nickel, as one might expect, but alongside them were astonishingly strong signals for niobium, rhenium, and hafnium refractory metals, with extraordinarily high melting points, elements that are exceedingly rare in typical asteroids. To find them concentrated in such a way was like panning for gold in a river and finding a solid, perfectly machined Swiss watch. These were not the ingredients of a primordial rock, they were the components of advanced high-temperature technology. They were the very materials we ourselves would choose if we were to build structures capable of withstanding the fury of a star. Yet even this paled in comparison to the central enigma. The isotopic ratio of the nickel present on its surface was wildly skewed. It was dominated by nickel 6-2, an isotope that has the highest binding energy per nucleon of any known element. In the heart of a dying massive star, this is the final, most stable stop on the assembly line of stellar nucleosynthesis. A structure built from nearly pure nickel-6-2 would be the strongest, most stable material against nuclear decay that the universe can manufacture. The surface of 3I, Atlas, was not just reflecting starlight, it was screaming a story of deliberate, sophisticated metallurgy. Dr. Vance, a scientist known for her unflappable composure, would later confide that upon seeing the final confirmed data, she felt a sensation she had never experienced in a laboratory, a deep primal sense of dread mixed with intoxicating wonder. The ghost in the machine was beginning to take on a terrifyingly solid form. While Vance's team was grappling with the object's material science, another group working with telemetry from the 500-meter aperture spherical telescope in China was deciphering a different kind of message. They were painting a portrait of 3I Atlas, not in light but in motion. They bounced powerful radio waves off its surface, listening to the faint echoes to map its shape and, more importantly, its rotation. Natural objects, especially irregular ones like asteroids, tend to tumble. They spin chaotically on multiple axes, wobbling through space like a poorly thrown stone. The initial low-resolution data on 3I, Atlas, had suggested a slow, somewhat irregular spin consistent with this model. But the new higher-fidelity data told a different story. As they refined the model, the apparent wobble vanished. The object was not tumbling, it was rotating with a serene, almost majestic stability. It spun on a single fixed axis, a rotation so clean and undeviating it was almost mechanical. It moved with the imperturbable poise of a gravitational gyroscope, a system in near-perfect equilibrium. This kind of rotational stability is incredibly difficult for a natural object of its shape and size to achieve and maintain. It implied something profound about its internal mass distribution. A homogeneous chunk of rock would not spin this way. To achieve such a state, the mass would need to be distributed with intention, perhaps with a denser core or a deliberately balanced structure, much like how engineers add weights to a car's tire to ensure a smooth rotation. The object's spin was not a chaotic remnant of its ancient formation. It felt damped, controlled, engineered. It was another piece of the puzzle that on its own could perhaps be dismissed as a strange coincidence. But when placed alongside the spectroscopic data from Chile, coincidence began to feel like a desperate, insufficient explanation. The two independent lines of evidence were not just anomalous, they were anomalous in precisely the same direction. They both pointed away from nature and toward artifice. The quiet speculation that had been confined to late-night coffee-fueled debates was about to ignite into a global intellectual conflagration. The spark that lit the flame was not a press conference or a leaked document, but a single 28-page paper uploaded to the academic preprint server RxIV. Its author was Dr. Aris Thorne, a theoretical astrophysicist at the Max Planck Institute, a man with a reputation for both unimpeachable rigor and a willingness to ask heretical questions. For months, Thorne had been quietly collating the disparate, strange data streams about 3I, Atlas. He had modeled its trajectory, which defied gravitational physics without invoking some unseen non-gravitational force. He had corresponded with Dr. Vance's team about the bizarre metallurgy and with the radio astronomers about the unnerving rotational stability. He saw what others had seen in pieces, but he assembled it into a single, terrifyingly coherent whole. The paper was titled with deliberate academic understatement, Anomalous Signatures of 3I, Atlas, an Inquiry into Parsimonious Explanations. Its argument was a masterpiece of scientific reasoning, a direct challenge to the institutional skepticism of his field. Thorne began by systematically listing every proposed natural explanation for the object's behavior. A hydrogen iceberg, a nitrogen shard, an exotic comet, a planetary fragment. For each one, he demonstrated how it failed to account for all times the observed data. The hydrogen iceberg would explain the acceleration, but not the lack of outgassing or the metallic signature. A planetary fragment would explain the metals, but not the impossible trajectory or the stable rotation. He showed that, to explain 3I, Atlas, naturally one needed to invoke a chain of increasingly unlikely ad hoc phenomena. You needed a unique type of object formed in a unique way which then experienced a unique set of circumstances to be ejected towards our solar system, all while maintaining its unique properties. It was, he argued, a violation of the fundamental scientific principle of parsimony, or Occam's razor, the rule that the simplest explanation is usually the correct one. Then, in the paper's devastating final section, he proposed an alternative. A single unifying hypothesis that explained everything in one elegant albeit staggering stroke. He argued that the object's thinness, its high tensile strength, its non-gravitational acceleration from solar radiation pressure, its advanced metallurgical composition, and its gyroscopic stability were not a collection of independent anomalies. They were in fact the predictable design features of a fragment of a specific theoretical megastructure. A piece of a shell built around a star to capture its energy, a shard of a Dyson Sphere. The paper landed like a thunderclap. Within hours it had been downloaded thousands of times. Email servers at universities across the globe lit up. It was all anyone in the astrophysics community could talk about. The reaction was immediate and violently polarized. The community fractured into three distinct camps. The first was the entrenched old guard who dismissed the paper as reckless sensationalism, a betrayal of the scientific method. They accused Thorne of leaping to an extraordinary conclusion without extraordinary evidence, arguing that unknown natural phenomena was still a far more likely explanation than aliens. They saw it as a dangerous flirtation with pseudoscience that threatened the credibility of their entire field. Then there was the second camp, a smaller but vocal group of primarily younger researchers who were electrified by Thorne's audacity. They argued that to ignore a hypothesis simply because it was profound was its own form of dogma. Science, they contended, must follow the data no matter how uncomfortable the destination. Thorne hadn't claimed proof. He had simply made a logical argument that the artificial hypothesis was now the times most times parsimonious, and that it deserved to be taken seriously and tested. They hailed the paper as a landmark of courage and necessary shock to a field that had become too conservative. And then there was the third and perhaps largest camp, the silent, conflicted middle. These were the scientists who, in the quiet of their own minds, admitted that Thorne had a point. They saw the elegance of his argument and the explanatory power of his hypothesis. They felt the same thrill, the same shiver of awe at the possibility, but they were also acutely aware of the professional risk. To publicly align oneself with such a radical idea was to gamble with one's reputation, one's funding, one's entire career. So they watched, they waited, they debated in closed-door meetings and private email chains, hoping for some new piece of evidence that would tip the scales decisively one way or the other. The intellectual thrill was palpable. For the first time in a generation, a question had been placed on the table that was so profound it touched upon the very core of our place in the universe. The controversy was no longer a quiet academic debate. The paper was discovered by the mainstream press, and the story exploded into the public consciousness. News headlines stripped of all scientific nuance screamed across the globe. Scientists claim alien megastructure found in solar system. The careful, cautious language of Thorne's paper was lost in a frenzy of speculation. The Dyson Sphere fragment hypothesis was no longer just a hypothesis. It had become a phenomenon. The sheer force of the debate created a new kind of gravity, pulling the world's astronomical resources into its orbit. The question of 3I, Atlas, was elevated from a niche curiosity to a global priority. At NASA, at the ESA, at Roscosmos, urgent meetings were convened. The data from Chile and China, while compelling, was still indirect. It was a silhouette, a shadow play. We were inferring the object's nature from its light and its motion. To settle the debate, to truly know, we needed to move beyond inference. We needed to see it. We needed a direct image, a photograph so clear and detailed that its nature would be undeniable. But the object was already far away, a faint speck receding into the darkness of interstellar space, far beyond the reach of any ground-based telescope to resolve its surface. Only one instrument in the human arsenal possessed the power to even attempt such an observation. A golden eye a million miles from Earth designed to see the dawn of time itself. The scientific community, once divided, was beginning to coalesce around a single audacious new goal. they would petition the directors of the James Webb Space Telescope for an unprecedented allocation of discretionary time. It would be the most difficult observation ever attempted, pushing the telescope to the absolute limits of its design. It was a long shot, a gamble of historic proportions. But we had to know. The burden of proof had shifted. The time for passive observation was over. The hunt was on. And so for a fleeting, incandescent moment, the idea burned brightly. The proposition that 3I Atlas was not a rock but a relic sent a tremor through the foundations of our cosmic solitude. It was a breathtaking leap, a narrative so grand it seemed to pull the very stars from their fixed positions to listen. But in the cold, clear halls of science, every dazzling new fire is met with the relentless force of a crucible. The more extraordinary the claim, the more fiercely the community will test it, seeking to melt away the fantasy and see what, if anything, remains of the truth. The exhilarating ascent to a radical hypothesis was over. Now began the long, arduous and necessary path downward into the unforgiving terrain of scrutiny. The first wave of skepticism did not come as a tsunami, but as a series of precise surgical strikes on the data, each one delivered by experts who had spent their lives studying the very kinds of objects that Atlas was supposed to defy. They did not mock the idea of extraterrestrial intelligence, for they were dreamers too in their own way. Instead, they offered something far more powerful, far more challenging to the Dyson Sphere fragment hypothesis, plausible, elegant, and entirely natural alternatives. The gauntlet was thrown down not with malice, but with a simple, profound demand that is the engine of all discovery: prove it. Prove that what we are seeing is not just a ghost in the machine, a misinterpretation of light and shadow, or more profoundly, a magnificent new piece of nature's own cosmic puzzle. The initial counterargument focused on the most basic assumption that we have seen all that the universe has to offer. Dr. Alistair Finch, a planetary scientist renowned for his work on the formation of solar systems, framed the challenge perfectly. He argued that we are like island dwellers who have only ever seen wooden canoes suddenly trying to explain a modern shipping container that has washed ashore. Our immediate impulse might be to attribute it to gods or magic, because it fits nowhere in our known world of woodworking. But the truth is simply that our world is far too small. We have only just begun to catalogue the sheer variety of objects drifting in the interstellar deep. Oumuamua was the first great shock, a bizarre cigar-shaped messenger that broke every rule we had for asteroids and comets. It taught us that the galaxy manufactures worlds with a diversity that dwarfs our own solar system's limited palette. Finch and his team proposed that 3I Atlas was not the second shock, but the next logical lesson in this ongoing cosmic education. Their theory posited that Atlas is an exotic interstellar asteroid forged in the heart of a star system profoundly different from our own. Imagine they urged a system born from a nebula rich in heavy metals orbiting a star with a violent, erratic youth. In this chaotic forge, planetesimals would form not from silicates and ice, but from almost pure iron and nickel compressed to unimaginable densities. Such an object would be a cosmic cannonball, a solid fragment of metal with a gravitational footprint far exceeding its visual size. This neatly explained one of Atlas's greatest mysteries, its mass. There was no need for hollow structures or alien alloys. Nature, in its boundless creativity, could have simply built a denser rock. This object would be dark, reflecting very little light, accounting for its faintness. And being a solid piece of metal, it would, of course, show no coma. It wouldn't outgas, because there would be almost nothing to release. It was a clean, simple explanation that relied on known physics merely expanding the list of possible ingredients. But what about the non-gravitational acceleration, the subtle, inexplicable push that seemed to be its calling card? Here the theory became even more ingenious. Finch's models suggested that an object with a highly irregular shape and a composition of nearly pure, unoxidized iron could interact with the solar wind and radiation pressure in ways we have yet to model effectively. If Atlas was spinning on a complex axis, a tumbling, lopsided pirouette, then different faces of the object would be heated by the sun at different times. This differential heating on a metallic surface could create a tiny, almost immeasurable recoil force, a phenomenon known as the Yarkovsky effect, but amplified to an unprecedented degree. Furthermore, the solar wind, a stream of charged particles from the Sun, could be interacting with its uniquely metallic surface, imparting a magnetic or electrostatic push that our models, which are based on dusty rocky asteroids, simply do not account for. It was a compelling vision, not a derelict starship, but a natural gravitational gyroscope being gently nudged through space by the breath of our own star. It required no aliens, only a broader imagination for what the universe considers normal. As this hypothesis gained traction, a second, even more dramatic natural explanation emerged from the field of planetary dynamics. This was the theory of the stripped core, and it was a story of unimaginable violence. It asked us to look back in time billions of years to a young, chaotic star system far away. In this system, a planet perhaps the size of Mars or Earth was just beginning to differentiate its heaviest elements, sinking to form a dense, molten core of iron and nickel, while a lighter mantle of rock and a crust of silicates formed around it. It was a world in the making, and then catastrophe. A collision of apocalyptic scale, a gravitational duel with a rogue planet or a close pass by its parent star, tore this fledgling world apart. Like a cosmic fruit being peeled, its crust and mantle were ripped away and scattered into the void, consumed by its star or flung into interstellar space. All that remained was the naked, fiercely dense heart of the planet, a planetesimal core now, a solitary wanderer, a cosmic shipwreck drifting through the eons. This theory, championed by astrophysicist Dr. Elena Vostok, was both terrifying and beautiful. It accounted for Atlas's density even more effectively than the exotic asteroid model. A planetary core would times be this dense. It would be this massive for its size. It would, for all intents and purposes, be a sphere or spheroid of solid metal, the toughest, most resilient part of a world, and the only part that could survive such a cataclysmic event and the long journey that followed. But the stripped core hypothesis had another crucial advantage. It provided a stunningly elegant solution to the mystery of the phantom push. Vostok's team argued that while the outer layers were stripped away pockets of highly volatile gases from the planet's formation, primordial hydrogen, helium, perhaps even noble gases could have been trapped deep within the metallic core, under immense pressure. For billions of years, these pockets would remain stable in the cold of deep space. But as Atlas began its journey through our solar system, the gentle but persistent warmth of the Sun would slowly penetrate its surface. Millennia of deep freeze would give way to a gradual thaw. Deep inside, those trapped gases would begin to expand. Eventually, the pressure would become too great, and tiny, imperceptible fissures in the metallic crust would open up, releasing focused jets of gas into space. These would not be like the great dusty tails of a comet. They would be focused, powerful, and most importantly, transparent. Jets of pure hydrogen or helium would be almost impossible for our telescopes to detect against the glare of the object itself. You would have a stealth thruster, a natural engine that pushes the object without leaving any visible exhaust. This could perfectly explain the non-gravitational acceleration. It would also explain why the push might seem intermittent or variable, as different gas pockets are heated and breached at different times. The theory was a masterpiece of cosmic forensics. It took all the disparate, confusing clues from 3I, Atlas, and wove them into a single coherent narrative of birth, destruction, and survival. It was a story just as epic as that of a Dyson Sphere fragment, but one scripted entirely by the laws of gravity and time. Against this powerful, dramatic, and utterly natural explanation, the idea of alien technology began to seem, well, a little bit desperate. It felt like reaching for magic when a perfectly good, albeit astonishing physical explanation was right there. Yet even as the momentum shifted towards these naturalistic models, a third group of scientists urged caution against abandoning the familiar too quickly. Their argument was simpler, less dramatic, but perhaps the most scientifically conservative. They proposed that 3I Atlas was in fact a comet, just a very, very strange one. We tend to think of comets as dirty snowballs primarily made of water ice. When they approach the Sun, the ice sublimates, turning directly into gas, which creates the beautiful glowing coma and tail that we see. The lack of such a coma on Atlas was one of the primary reasons for considering it an inert asteroid or something more exotic, But what if the comet wasn't made of water ice? Interstellar space is not uniform. Different regions are rich in different elements. A comet formed in a molecular cloud far colder and chemically different from our own Oort cloud might not use water as its primary volatile. It could be made of something else entirely. Solid nitrogen, for instance, which forms the glaciers on Pluto, or frozen carbon monoxide, or even more exotic ices. These substances sublimate at much lower temperatures than water ice. A nitrogen comet entering our solar system would have been active far out past the orbit of Saturn, long before our telescopes could get a good look at it. By the time it came close enough for us to study, much of its surface material might have already burned off. Moreover, the gas produced by sublimating nitrogen or carbon monoxide is transparent. It wouldn't create a dusty, reflective coma like water vapor does. It would outgas invisibly, creating that mysterious push without any of the traditional cometary signatures. This dark comet hypothesis was a powerful reminder of the principle of Occam's razor. The simplest explanation is often the best. Before we invent new categories of objects like stripped planetary cores or theorize about alien megastructures, shouldn't we first exhaust all possibilities within the categories we already know? Perhaps we hadn't found an alien probe, or the heart of a dead planet. Perhaps we had just found a new species of comet, a ghostly visitor whose chemistry was just different enough to fool us. The universe didn't need to break its own rules to create 3i, Atlas. It just needed to use a slightly different recipe. And this is where the true weight of the challenge lies. It's not one single alternative theory against the Dyson Sphere fragment idea. It is a phalanx of them. A diverse, robust, and scientifically rigorous set of explanations, each one plausible, each one backed by complex modeling, and each one rooted in established physics. Faced with this, the burden of proof becomes monumental. The late great astronomer Carl Sagan famously stated that extraordinary claims require extraordinary evidence. This isn't a catchy phrase, it is the absolute bedrock of the scientific method. It's a safeguard against our own most powerful and dangerous instinct, the will to believe. We want to find life. We want to believe we are not alone. This desire is so potent that it can color our interpretation of ambiguous data. It can make us see a signal in the noise, a pattern in the chaos. The demand for extraordinary evidence is the discipline we impose upon ourselves to ensure that what we find is real and not just a reflection of our own hopes. What would that extraordinary evidence even look like for 3i, Atlas? If we detected a repeating structured radio signal emanating from its surface, that would be a smoking gun. If our spectral analysis, the study of the light reflecting off it, revealed the presence of refined artificial alloys, not found in nature like pure titanium or complex metallic compounds, the case would be closed. If we could resolve an image of it, even a blurry one that showed unambiguous geometric shapes, straight lines, right angles, perfect curves, the debate would end. But we have none of that. All we have is a collection of anomalies of behaviors that are strange but not impossible to explain through natural means. Each oddity, its density, its acceleration, its lack of a coma is a piece of circumstantial evidence. And in the court of scientific opinion, you cannot prove a revolutionary case on circumstantial evidence alone, especially when the prosecution, the side arguing for a natural explanation, has such compelling stories of its own. To claim alien is the most audacious claim one can make. It means you have not only exhausted every single conceivable natural explanation, but you have also disproven them, and we are nowhere near that point. This entire debate is further complicated, shrouded in a fog of uncertainty, by the sheer frustrating difficulty of observing the object itself. This is perhaps the cruelest irony of the whole affair. We are grappling with one of the most profound questions in human history, and we are forced to do so by squinting at a single faint pixel of light. 3i, Atlas, is small, it is dark, and it is moving incredibly fast. From our vantage point on Earth, we are looking through a turbulent ocean of atmosphere that constantly blurs and distorts its image. Even our most powerful space-based telescopes are pushed to their absolute limits. Imagine trying to read the license plate of a speeding car at night in a blizzard from 100 miles away. That is the scale of the challenge. We can measure its brightness and how that brightness changes. From this, we infer its spin and get a rough idea of its shape. We can measure its position with astonishing accuracy, which is how we detected the non-gravitational acceleration in the first place. But we cannot see it. Not really. We cannot resolve its surface. We cannot see its features. The grand theories, the stripped core, the exotic asteroid, the alien artifact, are all built upon the interpretation of these faint, indirect signals. It's like trying to reconstruct the entire architecture of a cathedral by listening to the echo of a single handclap inside. The teams working on this are using every ounce of ingenuity they have. They are combining data from multiple observatories using advanced algorithms to cancel out atmospheric noise and pushing their hardware to the breaking point. But physics is a harsh mistress. There is a fundamental limit called the diffraction limit to how much detail a telescope of a certain size can resolve, and 3I, Atlas, is far, far too small and distant for our current technology to ever see as more than a point of light. This means we are trapped in a realm of ambiguity. The skeptics can argue that the phantom push is just a miscalculation in the Yarkovsky effect because we don't know the object's exact shape and spin. The proponents of the alien hypothesis can argue that the lack of a detected signal doesn't mean there isn't one, just that we aren't listening on the right frequency or that the artifact is dormant. Both sides can retreat to the shelter of the unknown. Both can point to the limitations of our own instruments as the reason the other side cannot prove its case. So we are left suspended between two worlds. In 1-3I, Atlas is a profound but ultimately natural cosmic messenger, a beautiful piece of celestial mechanics sent to teach us that the galaxy is stranger and more wonderful than we ever imagined. It is a story of physics, of violence, and of time. In the other world, it is the story we have been telling ourselves in whispers for centuries, the story of a first contact not with a living race but with their echo, a technological ghost haunting our solar system. The sober, cautious voice of science pulls us powerfully toward the first explanation. It is a world built on evidence, on precedent, and on the safe ground of the known. With the weight of established physics and a trio of compelling natural theories arrayed against it, the dream of a technological artifact seemed to be fading at risk of becoming just another cold, hard natural fact. The question was no longer just what is it had become a question of faith. Faith in the known patterns of the universe, or faith in the possibility of something entirely new. And for a while it seemed as if the case was closed, the mystery solved in favor of nature's awesome but impersonal power, until a new signal arrived, a faint whisper from the darkness that changed everything all over again. So, here we stand on the knife edge of a revelation, caught between a universe we thought we knew and one we can barely dare to imagine. For months we have pursued this phantom through the darkness, chasing a trail of baffling evidence that led us from the familiar shores of astrophysics to the wild, uncharted territory of speculation. We have dismantled every conventional theory, watched them crumble to dust against the intractable reality of 3I, Atlas. The cometry model failed its ghostly jets of gas and dust entirely absent from the crime scene. The hydrogen iceberg, a clever but desperate hypothesis, proved too fragile a snowflake in a furnace that would have vanished long before we ever saw it. Each natural explanation, each attempt to force this celestial anomaly into a recognizable box, has been met with a quiet, stubborn refusal. And in the void left by their failure, a single, audacious and terrifyingly elegant explanation remains a hypothesis that carries the weight of an entire civilization on its impossibly thin shoulders. The case for design for a deliberate and manufactured origin rests on a foundation of impossibilities. It begins with that signature unnatural drift. Witnessing its trajectory was like watching a ship sail without a breath of wind, a silent, effortless glide that defied the raw gravitational mechanics of the solar system. The sun's gravity was pulling on it, yes, but another force, a gentle, persistent pressure, was nudging it ever so slightly outward. This was not the chaotic, unpredictable thrust of a venting gas pocket. This was a force perfectly, exquisitely proportional to the inverse square of its distance from the sun. The push grew weaker as the object moved farther away, a signature so precise it felt less like a natural phenomenon and more like a mathematical proof being demonstrated across the heavens. This is the exact behavior predicted for a solar sail, a technology we ourselves are only just beginning to develop. It is the physics of pressure, not chemistry, of photons striking a surface, not ice turning to vapor. To explain this with nature requires a new unseen physics, or an object with properties we have never encountered. To explain it with technology requires only that somewhere, someone else is a little older and a little wiser than we are. Then comes the object's dignified, almost serene demise. When it began to fail, it did not erupt in the violent, messy conflagration of a comet nucleus, finally succumbing to the sun's tidal forces and thermal shock. There was no shrapnel, no expanding cloud of vaporized ice and ancient dust. Instead, it simply came apart. One solid object became two then, those two separated gracefully, continuing on their paths as if nothing had happened, still feeling that same anomalous push from the sun. It was less like an explosion and more like a structural failure, as if a rivet had popped or a cosmic weld had finally given way after a journey of unimaginable length. This clean separation, this lack of a chaotic debris field, is profoundly difficult to reconcile with a natural body. A tumbling, irregular chunk of rock or ice fracturing under stress should produce a spray of smaller fragments across a wide range of velocities. But 3I, Atlas, gave us something that looked unnervingly like a piece of equipment breaking down its constituent parts, drifting apart with an eerie mechanical calm. The scene lacked the elemental fury of nature. In its place was a quiet, cold, and ordered dissolution. Perhaps most damning of all is the silence of the thermal spectrum, the ghost in the thermodynamic machine. Every observation from every telescope powerful enough to get a reading told the same impossible story. The object was cold. It was inert. There was no significant outgassing to drive its acceleration, no sublimating surface of exotic ices boiling away into space. This single fact acts as the great filter, straining out almost every conceivable natural explanation. To move as it did, a natural object would have to be a celestial blowtorch, venting vast quantities of vapor. We looked for that heat, for that vapor, for the telltale chemical signatures of water, carbon monoxide, or nitrogen, and we found nothing. We were staring at an engine that was running but whose exhaust was invisible. This isn't just a missing piece of the puzzle, it is a gaping hole in the very fabric of the picture. The artificial fragment hypothesis, however, doesn't need that heat. A solar sail, a thin reflective sheet, would be pushed by sunlight alone, remaining cool and inert, perfectly matching the cold, silent profile of 3I Atlas. It fits the data not by adding new complexity, but by providing a chillingly simple explanation for the profound lack of it. When you weave these threads together, the impossibly smooth acceleration, the strangely ordered fragmentation, and the deep unnatural cold, the tapestry they form is deeply unsettling. It paints a portrait of a cosmic shipwreck, a derelict piece of starfaring technology tumbling through our solar system, a fragment perhaps of a once great Dyson Sphere, shattered in some ancient cataclysm, or simply degraded by eons of exposure to the harsh interstellar environment, a sliver of a shell built to surround a star, now a ghost ship sailing on the light of our own. This narrative aligns all the disparate, bizarre facts into a single coherent story. It feels right. It feels to some inevitable. It is the grandest, most profound explanation imaginable, and for a breathtaking moment it seems to be the only one that truly holds. And yet, for every argument that points toward the stars and whispers of intelligence, there is a counter-argument rooted in the deep soil of scientific skepticism that pulls us firmly back to Earth. The first and most powerful of these is a simple, beautiful, and ruthless principle that has guided science for centuries: Occam's razor. The idea that when faced with competing explanations, the simplest one is usually the correct one. And here, we must ask ourselves, in all intellectual honesty, what is truly simpler? Is it a new, as yet undiscovered class of natural object born from processes in the outer darkness of other star systems that we are only beginning to glimpse, or is it the remnant of a colossal, star-encompassing megastructure built by a Kardashev Type II civilization, which then shattered and sent a fragment on a billion-year journey to drift conveniently through our own backyard? The alien hypothesis is not by this measure simple. It is a pyramid of extraordinary assumptions, each one resting on the one below. It requires a civilization to have arisen. It requires them to have built something on a scale we can barely comprehend. It requires that structure to have been destroyed, and it requires a piece of it to have found its way to us. While the explanation feels emotionally and narratively simple, its underlying premises are perhaps the most complex imaginable. Then there is the profound and deafening silence. If 3i, Atlas, was a piece of technology, it was a remarkably quiet one. The search for extraterrestrial intelligence, SETI, has spent decades scanning the heavens, listening for the faintest whisper of a structured artificial signal. When this object appeared, it became a prime target. Radio telescopes, the grand ears of our planet, swiveled to listen. They strained to catch a ping, a beacon, a stray transmission from a dying power source, any sign at all that this was more than just rock and shadow. And what they heard was the same thing they have always heard, the static of the cosmos, the sound of silence. There were no techno signatures, no modulated radio waves, no focused laser light, no strange emissions in any spectrum. It was by all measures completely and utterly dead. This presents a difficult paradox for the alien artifact theory. How can we call something technology when it displays none of the active communicative properties we associate with it? Proponents might argue it's ancient, its power source long dead, but the absence of evidence is still a powerful data point, a heavy weight on the scale, tilting away from an artificial origin. It behaved like a machine, but it didn't talk like one. We must also contend with the humbling lessons of our own history. We have been standing at this precipice before. In the 1,960 seconds, astronomers discovered pulsars, objects emitting radio waves with such astonishing regularity that they were playfully labelled LGM1 for little green men. It seemed impossible that any natural object could be such a perfect clock. But they were not alien beacons. They were a new, incredible type of celestial object, a rapidly spinning neutron star, a cosmic lighthouse sweeping its beam across the universe. Then came the famous WOW signal. In 1977, a powerful narrow-band radio signal that for 72 seconds looked exactly like what we were searching for before it vanished forever, never to be heard from again. In each case, the universe presented us with a mystery that seemed to demand an extraordinary explanation, and in most cases the answer turned out to be extraordinary astrophysics, not alien engineering. This history does not disprove the possibility of 3i, Atlas, being artificial, but it serves as a powerful cautionary tale. It reminds us that our own imagination, our deep-seated hope to not be alone, can sometimes be a distorting lens. The cosmos has proven time and again that its capacity for generating natural wonders far exceeds our ability to predict them. This leads to the most plausible, if least exciting, rebuttal that 3i, Atlas, is simply something we have never seen before. Our catalogue of the universe is astonishingly incomplete. We have only been systematically surveying the sky for a tiny fraction of a single human lifetime. Is it so unbelievable that there are classes of objects out there we have yet to encounter? Perhaps it truly was a nitrogen iceberg carved from the frozen surface of an exopluto in another solar system possessing material properties, under interstellar conditions that our models failed to predict. Or maybe it was a type of cosmic dust bunny, an extremely low-density fractal aggregate of primordial dust light enough to be pushed by the sun, yet cohesive enough to hold its shape until it didn't. This unknown natural explanation is a catch-all, a box for phenomena that defy our current understanding. It feels unsatisfying because it lacks the specificity and grandeur of the alien hypothesis, but it is perhaps the most scientifically prudent position to take. It does not require us to invent new civilizations only to admit the limits of our own knowledge. It is the humble admission that the universe is more clever, more strange, and more diverse than we have yet given it credit for. So we are left suspended between two colossal narratives. On one side, the story of a cosmic voyager, a silent testament to life elsewhere, a message in a bottle without a message. Its physics are clean, its story compelling, and its implications would reshape the future of our species. It is a theory that satisfies our desire for meaning, for connection, for a sign that we are not a lonely accident in an indifferent void. On the other side, the story of our own ignorance. A story of a new natural wonder, a celestial platypus that breaks all our established categories and forces us to redraw our maps of what is possible. This narrative is less romantic, but it is a powerful reminder of the infinite frontier of discovery that still lies before us. It champions humility over hubris and patience over proclamation. The celestial jury has hung the evidence presented for both sides equally compelling and equally incomplete. The object itself offers no final testimony. It has crumbled into darkness, its secrets dissolving back into the void from which they came, leaving us with only the faint ghostly echo of its passage. What then is the truth of 3I Atlas? Is it the prosaic or the profound? A flaw in our understanding of nature, or the first confirmed whisper of intention from beyond our world? Perhaps the most powerful possibility is that it is both. It has become a cosmic Rorschach test, a blank screen onto which we project our greatest hopes and our most rigorous scientific doubts. It has forced two opposing sides of the human intellect into a brilliant, necessary conflict. The part of us that dreams, that looks to the sky and asks, "Are we alone?" has been given its most compelling piece of evidence yet. Simultaneously, the part of us that demands proof, that builds knowledge brick by painstaking brick, has been handed its most fascinating challenge. The object has, without a definitive answer, validated both the dreamer and the skeptic. It proved that searching for technosignatures is not a fringe activity, but a vital part of exploring the unknown. It demonstrated that objects with truly bizarre, seemingly artificial properties are times out there waiting to be found. The enigma of 3I, Atlas, is not a failure to find an answer. It is a gift of a better question. It has pushed the boundaries of our imagination outward, compelling astronomers, physicists, and engineers to think about what alien technology might actually look like, not as a gleaming starship from science fiction, but as a cold, dead, tumbling fragment indistinguishable from a rock until you look very, very closely. It has left an indelible mark, not with a crater, but with an unresolved tension that will fuel scientific inquiry for decades. Its fragments are gone, now vanishing into the interstellar dark, their light forever extinguished from our view. But the questions they carved into our sky, the profound uncertainty they illuminated, remain with us. They linger in the data, in the debates, and in the quiet moments of stargazing, a permanent and tantalizing reminder of the sheer, vast, and wonderful mystery we are only just beginning to unravel. And so, after its brief incandescent moment in our skies, the silence descends once more. The cosmic messenger, having delivered its cryptic pronouncement, continues its inexorable fall away from our star, away from the reach of our most powerful instruments. It recedes into the background, a diminishing point of light carrying with it the weight of our most profound questions. For us here on this lonely outpost of consciousness, the echo of its passage remains an indelible mark left not on the fabric of space, but on the fabric of human thought. We are left to grapple with the profound ambiguity it represents, a celestial sphinx that posed a riddle and then vanished before we could even begin to formulate an answer. Was it merely a breathtakingly strange, yet entirely natural cosmic shard, a fragment of an infant world, shattered in the chaos of its own system's birth, sent tumbling through the interstellar void for eons? Or was it something more, the echo of a purpose we cannot yet comprehend, a derelict piece of a colossal machine, the silent, glittering ruin of a technology so advanced it borders on the magical indistinguishable from nature itself? The truth is, we may never know for certain what 3I Atlas truly was. Its material form is now lost to us, a ghost sailing on the solar wind. But in a deeper sense, its ultimate classification has almost become secondary. The true lasting legacy of this object is not in what it times was times, but in what it has forced times us times to become. It has acted as a catalyst, a planetary scale shock to our imagination, and in its wake, three fundamental pillars of our cosmic perspective have been shaken to their very foundations. First and most dramatically is the search for extraterrestrial intelligence. For generations, SETI was an exercise in listening. We trained our vast radio dishes on the heavens, straining to catch a whisper in the static, a single structured signal that would betray the presence of another thinking mind. It was a passive search, a patient vigil kept by a species waiting for a call from across the cosmic ocean. 3I, Atlas, taught us that we might have been listening for the wrong thing. It suggested that the evidence of intelligence might not be a shout but a silent physical artifact, a piece of driftwood. It has given birth to a new, more audacious discipline artifact, SETI, a forensic investigation of the cosmos. Scientists are no longer just astronomers. They are becoming cosmic archaeologists, sifting through the incoming debris of the galaxy for anything that deviates from the expected, for any sign of manufactured, purposeful construction. This is a paradigm shift of monumental proportions. It forces us to ask entirely new questions. If a civilization builds on a galactic scale, what would its ruins look like? Would they be monolithic structures, or would they be countless trillions of smaller functional components scattered by time and catastrophe, like cosmic dust? Could the thin reflective material of 3I, Atlas, so perfectly suited to being a solar sail fragment, be the equivalent of a single potsherd from a forgotten city, a single luminous brick from a fallen Tower of Babel that once reached for a distant star? The search is no longer just for a living, breathing contemporary. It is now also a search for the ghosts of the galaxy, for the technological fossils of civilizations that may have risen and fallen long before life on Earth had even crawled out of the primordial seas. This single object has legitimized a field once relegated to the fringe, transforming it into a rigorous predictive science. We are now actively modeling the spectral and dynamic signatures of hypothetical megastructures of alien probes of industrial waste. We are building the intellectual toolkit needed to recognize the artificial even when it comes in a form so strange it barely registers. The great silent filter of the cosmos may not be a barrier to life's emergence, but simply the unimaginable gulf of time that separates civilizations. 3I, Atlas tantalizingly suggests that the evidence of their existence might be drifting past our front door if only we have the wit to see it. The second pillar to be shaken is our understanding of planetary science itself. Even if you strip away all speculation of intelligent origin, 3I, Atlas, remains a profound anomaly, a scientific unicorn. Our models of how solar systems form and evolve are built on the evidence we have gathered from our own neighborhood and the distant light of thousands of exoplanets. These models are robust, but they have their limits. They predict what a normal piece of interstellar debris should look like. It should look like Oumuamua, a dark, rocky or icy body. It should not be a vast, gossamer-thin sheet of highly reflective material lighter than anything we believed could naturally condense and survive the brutal journey between the stars. This object challenges the very core of our theories on planetesimal accretion. How could such a fragile, low-density structure form in a protoplanetary disk? What forces could eject it from its parent star without shattering it? How could it endure millions, perhaps billions of years of relentless cosmic ray, bombardment and radiation pressure? Its existence is a statistical improbability that borders on the impossible given our current understanding. And that is precisely why it is so valuable. In science, it is the outliers, the data points that don't fit the curve that signal the path to a deeper truth. They reveal the hidden assumptions and the undiscovered physics lurking just beyond the edges of our knowledge. Planetary scientists are now scrambling to devise new models, to imagine new forms of cosmic geology and chemistry that could give birth to such an object. Could metallic-rich gas in a unique stellar environment condense directly into ultra-thin foils? Could the explosive death of a peculiar type of star produce such ethereal shrapnel? These are no longer idle speculations. They are urgent lines of inquiry, entire careers pivoting to solve the puzzle presented by this one fleeting visitor. 3I, Atlas, has become a cosmic whetstone, sharpening our theories by forcing them to account for its bizarre properties. It reminds us with brutal humility that the galaxy is not just a larger version of our solar system. It is a vast and varied ecosystem of stellar environments capable of producing wonders that beggar our imagination. We thought we knew the catalogue of what was possible. This object arrived, and gently, silently tore the catalogue to shreds. And that leads us to the third and perhaps most profound impact, the blow to our own perception of humanity's place in the universe. For centuries, we have operated under a quiet, unspoken assumption that the boundary between the natural and the artificial is absolute. A rock is a rock, a machine is a machine. We look at the intricate fractal beauty of a snowflake and the stark geometric lines of a skyscraper, and we see two fundamentally different orders of existence. One is born of mindless physics, the other of deliberate intent. 3i, Atlas, collapsed that distinction into a quantum superposition of possibilities. It exists in that liminal space, that uncanny valley where the products of nature become so exquisitely strange that they appear to be engineered, and where a hypothetical technology becomes so advanced it is indistinguishable from a natural phenomenon. This is a deep and unsettling philosophical challenge. It forces us to confront the limits of our own epistemology. How can we ever truly know if we are looking at a natural marvel or an artifact from a Type 3 civilization? What is the ultimate test for intentionality when the creators may operate with a physics and a purpose so far beyond our own? This object has held a mirror up to our own cognitive biases, to our tendency to see patterns and intent where there may be none, but also to our failure of imagination in considering what might be possible. It is a humbling lesson in cosmic modesty. It tells us that we are still in the infancy of our explorations, that our knowledge is a tiny, flickering candle in an infinite darkness, and that the universe is under no obligation to make sense to us. The feeling it leaves behind is not one of fear, but of awe at the sheer, boundless creativity of the cosmos, whether that creativity is expressed through the blind watchmaker of physics or through the hands of a forgotten intelligence. The mystery of 3i. Atlas is now part of our cultural story, a modern myth that encapsulates our hopes, our fears, and our unquenchable desire to know that we are not alone. The visitor may be gone, but the questions it ignited burn brighter than ever. And now, finally, we are building the tools to answer them. Our encounter with 3i Atlas was a wake-up call, revealing the glaring inadequacy of our current planetary surveillance systems. We were caught by surprise. We saw it too late. We lacked the ability to react to study it in the detail it demanded. That era is now coming to a close. A new generation of sentinels is rising across the globe, designed not just to map the stars but to watch the spaces in between. The first of these is already changing the game from its perch a million miles from Earth. The James Webb Space Telescope, with its unparalleled infrared sensitivity, can dissect the faint thermal glow of interstellar objects, giving us clues to their composition and internal energy sources that were previously unthinkable. Had Webb been watching 3i Atlas, we might have known if it was a uniform cold sheet or if it harbored hotspots of hidden technology. But the true revolution in detection is about to begin in the high desert of Chile, here the Vera Sea. Rubin Observatory is nearing completion. This is not just another telescope, it is a cosmic motion detector. Its massive camera, the size of a small car, will scan the entire visible sky from the southern hemisphere every 3 nights. Every 3 nights. It will generate a torrent of data so immense it has been called a digital fire hose, producing a motion picture of the universe instead of a series of static snapshots. Its legacy survey of space and time, the LSST, is predicted to increase our detection rate of interstellar objects by a factor of 10 or 100 or perhaps even more. We will go from finding 1 or 2 per decade to potentially dozens every single year. They will no longer be rare, shocking apparitions. They will become a steady stream of visitors, each one a unique data point, a new piece of the puzzle. The Rubin Observatory will be our early warning system, spotting these travelers while they are still far out, giving us the precious time we so desperately lacked with Oumuamua and Atlas. Time to prepare, time to observe. And, as the Rubin Observatory finds them, a host of other new eyes will be ready to turn and stare. On the ground, behemoths like the extremely large telescope and the 30-meter telescope will come online. Their gargantuan mirrors, tens of meters across, will act as cosmic light buckets of unprecedented scale. They won't just take a picture, They will perform high-resolution spectroscopy, slicing the faint reflected sunlight from these objects into a rainbow of data. They will be able to identify specific minerals, organic compounds, and even isotopic ratios. This is where the search for artifice will become exquisitely precise. Does an object contain elements or isotopes in proportions that defy any known stellar nucleosynthesis? Is its surface made of a pure, refined metal alloy, rather than the chaotic jumble of a natural asteroid? These telescopes will have the power to turn a tantalizing hint into a robust scientific conclusion. In space, the Nancy Grace Roman Space Telescope, with a field of view 100 times larger than Hubble's, will conduct its own sweeping surveys, potentially finding interstellar wanderers that the ground-based observatories might miss. Yet, even with this arsenal of new observatories, we are still just watching from the shoreline as the messages in a bottle drift by. The ultimate goal, the dream that 3i, Atlas, has crystallized into a tangible ambition, is to reach out and touch one. To move from passive observation to active in situ investigation. And for that we need a new class of spacecraft. The European Space Agency is already preparing one such mission, the Comet Interceptor. It is a masterpiece of patient engineering. The spacecraft will launch and then park itself at a stable point in space, entering a state of hibernation waiting. It will wait for the Rubin Observatory, or another survey, to discover a pristine long-period comet, or ideally a new interstellar object on a trajectory that is reachable. When the alert comes, Comet Interceptor will awaken. It will fire its engines and begin a high-speed chase, a precisely calculated ballet of orbital mechanics to rendezvous with the target millions of kilometers from Earth. It will be the first time we have ever visited an object fresh from the interstellar abyss, its surface untouched by the searing heat of our sun. But even this incredible mission has its limits. It can only reach targets with favorable low-energy trajectories. What about the next Oumuamua? The next 3i, Atlas objects, moving at incredible speeds, whipping through our system on paths that no conventional rocket could ever hope to match. For those, a far more audacious concept is taking shape. It is called Project Lyra. Proposed by the Institute for Interstellar Studies, it is a plan for a high-speed interceptor probe, a true interstellar hunter. The concept involves using a massive rocket like NASA's Space Launch System or SpaceX's Starship to launch a probe on a direct course towards Jupiter or the Sun itself. The probe would then perform an extreme gravity assist maneuver, a powered Oberth maneuver, firing its own engines at the point of closest approach to gain a truly colossal boost in speed. It would be a spacecraft shot from a gravitational slingshot flung out into the solar system with enough velocity to chase down and catch even the fastest interstellar visitors. It is a mission profile fraught with extreme engineering challenges, pushing the very limits of materials science and propulsion technology. But it is no longer science fiction. It is a serious proposal, a reflection of how deeply our priorities have shifted. The ambition to send a piece of humanity to another star system is now matched by the urgent desire to intercept a piece of another system that has graciously come to us. Ultimately, this is the enduring legacy of that fleeting visitor. 3i, Atlas, whether natural artifact or alien relic, has done something more important than providing an answer. It has bequeathed to us a more magnificent question. It has reinvigorated our sense of wonder, reminding us that the age of exploration is not over. The great uncharted territories are not on our own world, but in the vast, silent ocean that laps at the shores of our atmosphere. We are building the ships to sail that ocean, the lenses to peer into its depths, and the intellectual courage to face whatever we might find there. The truth is still out there, written in the trajectories of silent wanderers and the spectral lines of their reflected light. And for the first time in our history, we are finally truly ready to read it. The search has just begun.